Welcome to The Explainer. Today, we're diving into one of the most beautiful and, one of the most controversial ideas in all of physics, supersymmetry. It's this incredible theory that could solve some of the deepest puzzles we have about the cosmos. But there's a catch. After decades of looking for it, we found nothing. And that puts this beautiful idea on trial.
All right, so let's get right into it. To even understand why physicists dreamed up something as wild as supersymmetry in the first place, you kind of have to appreciate this deep puzzle that's sitting at the heart of everything we know. It's this weird feeling that the universe is just balanced on a knife's edge.
You know what? This picture, right here, it pretty much says it all. See, our best theories tell us that a really important particle, the Higgs boson, its mass should be totally out of whack because of all these crazy quantum effects. But it's not. The number we actually measure is incredibly stable and precise. It's like it's been perfectly, delicately placed there against all odds.
And look, this isn't just physicists being picky. It's a huge mathematical problem we call the hierarchy problem. I mean, to get the Higgs mass that we actually see, the numbers in the equations have to be tuned with the precision of 1 part in 10 to the 32. That's like measuring the distance to the edge of the known universe and getting it right to within the width of a human hair. A fine-tuning like that, to a physicist, that's not an answer. It's a giant flashing sign that we're missing something big.
So what is that missing piece? Well, this question leads us to one of the most ambitious ideas ever proposed, supersymmetry. You'll often hear it called SUSY for short. And what it suggests is that the universe has this incredible, hidden symmetry that we just haven't been able to see yet.
So what is SUSY, really? At its heart, it's the idea that there is this deep, profound connection between the two fundamental kinds of particles that make up, well, everything.
Okay, so in our current model of the universe, we call it the standard model. You basically have two totally different teams. On one side, you've got the fermions. These are the bricks. They're things like electrons and quarks, the stuff that builds all the matter you and I see. Then on the other side, you have the bosons. They're like the mortar holding it all together. They carry forces. Photons, which make up light, are a perfect example. Right now, these two teams live in totally separate worlds.
But supersymmetry? Oh, it completely changes the game. It says that for every single particle we know and love, there's a secret superpartner hiding in the shadows. And this simple idea, this pairing, it has a radical consequence.
And here it is. This is the magic trick that solves the whole fine-tuning problem. For every matter particle, like the electron, SUSY says there's a force-carrying partner called wait for it, selectron. And for every force particle, like a photon, there's a matter-like partner called a photino. Now, the crazy quantum effects from these new partners perfectly cancel out the instabilities from the old ones. It just happens automatically. All of a sudden, the universe isn't fine-tuned at all. It's just naturally balanced. It's beautiful.
Okay, so that, of course, raises the billion-dollar question, right? If this whole mirror world of particles is real, where is it? Well, the leading theory is that these superparticles are incredibly heavy, so heavy that you need the insane energies of our most powerful particle colliders, or the kind of energy that was only around in the first fiery moments after the Big Bang, just to create one.
And the fact that we don't just see selectrons floating around with the same mass as electrons, well, that tells us something absolutely crucial. It means if SUSY is real, it has to be a broken symmetry. Think of it like a perfect, beautiful snowflake. In the super-hot early universe, the symmetry was perfect. But as everything cooled down, that symmetry shattered, leaving the superpartners much, much heavier than their everyday counterparts.
But you know, for a lot of physicists, fixing the Higgs mass is just the warm-up act. The real magic of supersymmetry is that it seems to be a key that could unlock an even bigger prize, a unified theory of everything. And that includes gravity.
Now this is a truly mind-bending insight. It turns out that if you take the rules of supersymmetry and you say, okay, these rules have to work at every single individual point in space-time, what physicists call making the symmetry local, something absolutely incredible happens. Gravity just appears. It pops right out of the math. You don't have to add it in, the theory demands it.
And this logical chain, right here, is why so many of the world's smartest people have been obsessed with this idea for decades. Supersymmetry stops being just a neat fix for the standard model. It starts to look like a necessary stepping stone, a required piece of the puzzle to get to the leading candidate for a theory of everything, string theory. It's like finding a piece of the universe's underlying blueprint.
And that brings our story right up to today. Because for all of its mathematical elegance, for all of its incredible promise, Supersymmetry is now facing its toughest judge: cold, hard, experimental reality.
So here's the rub. For years, we've been smashing particles together at the Large Hadron Collider, the most powerful machine ever built, recreating those early universe energies for the specific purpose of finding these superpartners. And we have found absolutely nothing. Not a hint. And this is forcing a real moment of reckoning in physics. Are theorists just, tweaking the models to keep the particles just out of our reach? Or is it time to admit that this beautiful idea might just be wrong?
And that, right there, is the cliffhanger at the very edge of modern physics. Is supersymmetry, this beautiful truth about reality, just waiting for us to build a slightly more powerful experiment to finally uncover it? Or is nature trying to tell us that the universe is far stranger and maybe a lot less symmetrical than we ever dreamed? The next big discovery won't just be about finding a new particle. It's going to tell us what kind of universe we're really living in.